Hi, I'm Ashim Datta. I'm a professor in the Department of Biological and Environmental Engineering at Cornell University. This short module is one in a series intended to help recap the math that might have been done a year or two earlier before taking an undergraduate course on heat conduction or mass diffusion. So this particular module is simply a summary of three different cases. So we are considering the homogeneous heat conduction equation in Cartesian coordinate without the time derivative, meaning we are only talking about solution to this equation. It can't get any simpler. So in the following slide, we're going to talk about the solution to that equation for three different boundary conditions. So let's see. We are trying to solve d squared t dx squared equal to 0. And the boundary condition, we need two of them. As you can see, it's second derivative. And one condition is same for all three cases. The other one is different in each case. So t at x equal to L is t2, where the value is given. Then in this case, it's the derivative that is given. Minus k dt dx is equal to q. So this is constant, and this is a value that is also constant. So in other words, dt dx is given here, and this third one is sort of a combination of the first two. So this one looks like minus k dt dx at x equal to L. By the way, this is also at x equal to L is equal to h times t at x equal to L minus t infinity. And so this is the condition at x equal to L in this case. Now you may wonder, why are we doing these kinds of situations? Because they represent very clearly certain types of physics. So they come from physics, so they're real. So we're going to need to solve for these conditions. So the solution for these two boundary condition looks like this: t equal to t2 minus t1 times x over L plus t1. And in this case, the solution, or let's plot this one. So t at x equal to 0 is t1, and t at x equal to L is some t2, and the solution is linear. In this case, in the second case, the solution, if you can really do this very easily in a few steps, plus t1. So if we plot this, this is x equal to 0. At x equal to 0, it is t1, and x equal to L, whatever value it is, but I know the slope. So this slope, this is the slope of the line, and whatever t2 that leads to, that we can figure out, but it is the slope that is given. Okay, so in the third case, the solution is t equal to h times t infinity minus t1 over k plus hl times x plus T1. Okay, so if we plot this one again at x equal to 0, it's T1, and then at x equal to L, whatever value we can figure out from the equation, but the point is the solution is given by this slope. So we have a point here and the slope, so that gives me the solution. So what is the big thing that we want to take from this? You notice that all three, this one, this one, this one, they're all solutions of one equation. In fact, one of the boundary condition is also the same in all three cases. But just because we change the other boundary condition, the solution is different. So changing boundary condition changes the solution. It's very obvious, but this has major implications as we do physics. The physics is very different as represented by the solutions. We did this for the Cartesian coordinate, but the same thing would be true if we solve the equation, the corresponding equation in cylindrical coordinate or spherical coordinate. If we change the boundary condition, then the solutions would all be different. Thank you.